start off this video, let's go over the challenge problem from the last video. So we have two balls thrown upwards in the same gravitational field. That means they have the same acceleration. Ball B is thrown with twice the initial velocity of ball A. How much higher will ball B go than ball A? Alright, so let's make a chart of what we know. We know that this is going to be for ball A. Ball A has an initial velocity, VA, and we're looking for the maximum height. So that means it's going to have a final velocity of 0, has an acceleration of g, and we are looking for delta y. Ball B is going to have an initial velocity of twice that of ball A. So we're going to say 2VA. Going to have a final velocity of 0, acceleration of g, and we're also looking for delta y. So we don't really have anything involving time in this problem, so let's use one of the kinematic equations without time. So that would be final velocity squared equals initial velocity squared plus twice the acceleration delta y. Right, immediately we know that final velocity is 0, so we can cross that out. And now let's solve for delta y because we are looking for height. So that would make delta y equal negative of the initial velocity squared divided by 2a. Right? Well, we know that 2a is going to be the same for both of these balls. However, the initial velocity is not. So let's do a little bit of division. I want to do this problem in a more formal way. So we're going to take delta y of ball B and divide it by the delta y of ball A, right? So we know the initial velocity of ball B is going to be negative twice the initial velocity of A squared divided by 2g, and that for ball A we're going to have negative VA squared divided by 2g. Alright, now just let me make some room really quick. We don't really need this chart anymore, so I don't want to get rid of that. Alright. Alright, that should work. Alright, so I'm going to multiply the numerator and the denominator by 2g so that will cancel out of the equation. These negatives will also become positives, and then we're just going to square. So we have change in yb over change in y of A is going to equal 4VA squared over VA squared, and that leaves us with this 4. So that's going to tell us that ball B is going to go 4 times higher than ball A when it is thrown with twice the initial velocity of ball A. So this video is going to be an introduction to forces, and let's start by defining a force to be a push or a pull on an object. So for example, here I have a box. So we could have a person here that pushes on the box, or we could have a person here who is pulling on the box, right? And there is an equation to describe forces. It's called Newton's second law. We'll get to Newton's other laws in a moment. And that states that the net force on an object is equal to the mass of said object times the acceleration of said object. And notice these vector symbols. That means force has both a magnitude and a direction. It can be negative, and so is acceleration. So let's go back to this box here. Notice that I said net force. Net force is the sum of the individual forces. So let's call this person A and this person B. Alright? Person A is pushing on the box to the right, and person B is pulling on the box to the right. So there is a net force on the box to the right. Alright, and maybe we want to calculate the acceleration of this box, right? So let's say that person A is pushing with a force of 10 newtons, and person B is pulling with a force of 5 newtons. So we want to solve for acceleration, and let's say this box has a mass of 3 newtons. So first let's start by solving for acceleration, and we're going to say acceleration equals the net force, I'm going to put a little n sub n for net, divided by the mass of the box. So the net force is going to be the force of person A plus the force of person B divided by the mass of the box. And we are not concerned about the mass of person A or person B. That does not go into this equation. It's the mass of the object whose acceleration we're solving for. So we're defining right as positive. So person A is pushing with a force of 10 newtons. Person B is pulling with a force of 5 newtons. And the box has a mass of 3. This should be 3 kilograms, not 3 newtons. Right, so then we are left with 15 over 3, and that gives us 5 meters per second squared. So that would be the acceleration of the box. Right, now another thing I really want to go over quick is the units for force. You'll notice that I mentioned newtons. So we know that F equals ma, right? So we know that a mass is measured in kilograms in our standard units. Acceleration is measured in meters per second squared. So that means 1 newton is equal to 1 kilogram times meter per second squared. And that's how we got our units for acceleration. So when analyzing forces, sometimes what can happen is that you get components of forces. For example, say I have a box on the ground and I have a string attached to it, right? But this string is pulling at an angle, say theta, from the horizontal. And maybe I want to know the acceleration of the box in the horizontal direction. But to do that, I need the horizontal component of tension. So that at that point, we would take the tension times the cosine of the angle. Because if you remember from trig, cosine would be the adjacent side to the angle, so the horizontal direction, divided by the hypotenuse, which would be tension. So at this point, we get into something called free body diagrams, and that just helps to make sure that we are looking at all of the forces involved on the object and we're not forgetting one. So let's go through a free body diagram. Say for this object, let's make it another box, and it is suspended from the ceiling by 2 strings, right? And I'm going to draw a free body diagram for this object. So first we start with a dot, and that represents the center of mass of the object, and then we look at the forces acting on that center of mass. So the best way to start is usually what is in contact with this box, what is touching it. Well, we have one component of tension, we'll call that T1, and we'll match it with the one on the diagram. And then we have a second component of tension, we'll call that T2. And those are the only forces that are touching the object. Now, what about forces that aren't in contact with that object, such as force of gravity from whatever planet we're on, let's just say Earth. So that acts straight down towards the center of the Earth, and we're just going to call that F sub E for the force of Earth on that object, because the Earth is what is exerting that force of gravity. Now, at this point, it would be a lot easier to solve than just looking at the diagram, because we know exactly what forces we have. Another thing with free body diagrams is that on the AP exam, never draw a free body diagram with your components. For example, let's say I did this and I did T2 sub y, and then maybe I did a T1 sub y because they're both acting upwards, and then I did a T2 in the horizontal direction, and then I did a T1 in the horizontal direction, and then I drew my force of gravity, or the force of the Earth. If that is the way you have to do it, that's fine, but make sure you always do this one first, and then you do this one second, separately, and not, if they give you a dot to draw your free body diagram on, do not do components on that one. Alright, let's run through a practice problem. So we're going to have, let's say, a box on a horizontal surface, and we're going to have a force here at, say, an angle of, let's do 30 degrees. And let's say this box has a mass of 10 kilograms, and the force of tension is 6 newtons. I want to figure out what is the normal force. And let me rewrite that really quick. What is the normal force? So the normal force basically is a force that always acts perpendicular to a surface, right? So in this case, it would be going like that, and that's really the force of the ground on the box. Like, for example, if you had an incline, this would be the normal force. We will get more examples with that when we do our video on pulleys and inclines. Alright, so what is the normal force? The first step is to make a free body diagram. So free body diagram, let's say this is our dot. So what are the forces in contact? Well, we have the normal force. That is typically denoted F sub n for normal. And we have the force of tension. The force of tension acts at an angle, so we're going to draw it at an angle. So we're going to call that F sub t. And we also have the force of the Earth. Oh, yeah, we're going to say this is on Earth. Right, this is not to scale. They don't have to be to scale unless specified. Okay, now we want to figure out normal force. And we know normal force acts in the vertical direction in this example. Right? And remember that our net force equals mass times acceleration. Alright, so let's sum up our forces in the y direction. So what forces act upwards? We're going to call upwards our positive direction. Alright, well, we know we have the normal force acting upwards. Anything else? Tension, right? But tension is at an angle. So we have to take, we want the vertical component. So we're going to take plus F sub t sine of our theta. Those are the only forces acting upwards, and then downwards we have the force of gravity, or the force of the earth. But this box is at rest, right? So acceleration is equal to 0, and anything times 0 is 0, so all of that equals 0. Now we can solve for the normal force to get the force of the earth. Minus ft sine theta and now it's really just a matter of substituting in values. The force of the earth is equal to the weight of the box, so this would be mg. Force of tension would be minus t sine theta, sine of theta. Substitute in values. So 10, and we're going to use the gravity as 10, so 10 times 10 is 100. Force of tension is 6, sine of 30 is 1/2, so this comes down to 100 minus 3, so that would make the normal force 97 newtons. But there is a bigger lesson here. Notice that when you have this force of tension acting upwards, you have a vertical component of tension, that the normal force becomes less than the weight of the box, because the normal force doesn't have to balance the entire weight of the box. Now it only has to balance its component. So in this case, the force of the earth is greater than the normal force. The weight of the box is greater than the normal force. But that's only possible because we have that vertical component of tension there to make up for the difference. Alright, for this last example, let's say we have a cart and let's say the rotation of the wheels is like negligible and there's no friction or anything. Let's say we have a force acting this way at an angle of 60 degrees with a force of tension of 12 newtons. And then let's say we have a force of tension here with, say, 8 newtons. I want to know what is the acceleration of the cart. So we're going to solve for acceleration, and let's give it a mass of 5 kilograms. Alright, first, let's start with a free body diagram, and these are going to stick with you for pretty much the rest of the physics, in AP Physics 1 and 2, and probably more in the future too. So get lots of practice for these. So our dot for the center of mass, what forces are in contact? We have a force of tension here. I'll call that T sub 1. And I'm going to mark it here. And we have a T sub 2. Gonna do that one here. We also have a normal force. Any forces that are not in contact, got the force of the earth. Let's just say, unless otherwise specified, all of these problems are going to be taking place on Earth. Alright, and acceleration would be in the horizontal direction. So let's sum our forces in the horizontal direction, and let's just call typical right positive. So we've got T2 to the right. That's the only force acting to the right. But to the left, we have a horizontal component of our T1, and we can see that from our free body diagram. And horizontal goes with cosine, but that's in the negative direction, so we do minus T1 cosine of theta is going to equal ma, right? So if you divide both sides by mass, you will get acceleration. Alright, now we can just substitute in our values. So we have a value of 8 newtons for T1 minus or for 8 newtons for T2, T1 is 12 newtons, and cosine of 60 is 1/2. So we'd have minus 6 newtons to the left, divided by a mass of 5 kilograms, to give us an acceleration of 0.4 meters per second squared. Alright, now I did this problem for a reason too. This does not mean the car is moving to the right. Okay, we have two options to describe its motion. So one, we could say it's moving to the right and speeding up. But that is not the only option. Alright, it could have an initial direction of motion to the left with an acceleration to the right and slowing down. Alright, this just tells us the acceleration. We know nothing about its initial velocity. So just keep that in mind, that unless you are given initial values for velocity and you just know the acceleration, that you can't claim the car is moving in one direction or the other, because here we got two equally possible options. Alright, for the challenge problem for this video, I want you to decide and figure out which of these strings would be most likely to break in situation A, B, or C, and justify your answer. The solution will be on my Instagram page about 24 hours after the release of this video, or you can find it at the beginning of the next video. And I'll give you a little hint: draw free body diagrams for each of these boxes.